The next speaker is Konstantin Olmezov, and the topic of his talk is an elementary approach to the operator method in additive combinatorics. And Konstantin, you can start.
Okay, yes, I start. I will talk about finite sets in abelian groups, and we study the additive energy of sets that define as a number of solutions to typical additive equations, and for technical reasons, some types of energy, such as common energy and higher energy, and additive combinatorics study extremal values of energy, in particular extremely small values. Important families of such sets, of sets for which we study energy, is so-called convex sets of real numbers and sets with few products. General conjecture about these sets state that all such sets have extremely small value of energies, and for such sets exist very good results about higher energy and about common energy with arbitrary other set D. In certain year, Ilya Shkredov provide a special operator method for obtain non-trivial conclusion from this result using popular differences as set D. Main part of Shkredov proof is a very general lemma about a relationship between number of solutions for two systems of linear equations. Let's denote a number of solutions at concept of Iverson notation. Then you can see statement of lemma on slide. Main property of this lemma, of this inequality, is some cycle structure of common variables in right system. You can see that we have transition from x to y in first equation, from y to z in third equation, and back from z to x in second equation. Now I will provide a very simple elementary proof of Shkredov's lemma from two steps, instead of proof by operator method. We use Cauchy-Schwarz inequality and two important conclusions for bounding number of solutions. We say that we use mirroring principle if we use bounds in terms of symmetric equation, and we say that we use coping principle if we use bounds in terms of two copies of equation with new common variable. Let's apply coping principle to equation of additive energy, and after it apply mirroring by so-called diagonal of this system. I try to illustrate it on slide. We split system by diagonal, formally fix value of difference and the value of variable that denoted by Z and D on slide. And we apply Cauchy-Schwarz inequality by to summing by these two variables. It fully completes proof of Lemma just in 2 steps. And now I will discuss graph interpretations of this proof. Let's define the convolutions multigraph of a finite set as graph that have vertex set equal to A, equal to finite set, and that have a number of H's from X to Y equal to convolutions of X minus Y. Notice that number of solutions to different system equations, that we used in proof of Schrodinger's lemma is in fact a number of triangles and numbers of cherries in such graph. And it is useful to illustrate graph transition from triangle to cherry by Cauchy-Schwarz inequality. Just write triangle system and rearrange variables inside each equation such that we obtain rearrange variables inside each equation to obtain some symmetric structure inside each equation. After it, we can notice some symmetric in graph and notice that this symmetry can be expressed as square in inner sum on formula over picture. And same technique we can apply to equation of additive energy, split to 2 parts. And about merging these pictures, we can see that we can interpret it as result of applying Cauchy-Schwarz inequality. We can move parts of symmetry from each other, and we can complete splitted edge of triangle by halves of edges from energy, such it illustrated on the slides. Of course, to obtain a correctly sequence of Cauchy-Schwarz inequality, we need add normalizing factors to formulas over pictures such that different powers of size of A. And such interpretation turn us to considering Sydor-Yankees conjecture. Sydor-Yankees conjecture study a number of homomorphisms from some small graph H to some big multigraph G, and summing all products of number of edges inside each such homomorphism. We can again notice that a number of such homomorphisms from triangle H to convolutions graph of init sets is in fact right side of Shkredov's inequality. And Sidorenko's conjecture states that for bipartite graph H and any multigraph G, number of such homomorphisms is at least same that should be expected for random graph on same set of vertices and that have same density.
I'm sorry, what is the K2?
K2 is a graph with two vertices and one edge. Full graph on two vertices. And Sidorenko conjecture assume that H is bipartite graph, and it important assuming. It is important assuming, but as we see, for special case when G is convolutions graph, we can prove analog of Sidorenko's conjecture for triangle H that, of course, is non-bipartite. This turns us to state extended conjecture that state that for any graph H and any finite set A, Sidorenko conjecture is true at context of given H and convolutions graph of given set. In particular, we already proved a case with triangle H of extended conjecture, and now I will provide construction of infinitely many non-bipartite graphs for which we can prove extended conjecture also. Let's consider trivial approach to Sidorenko conjecture when we can fix independent set of vertices from H and separate summation by these vertices to outer sum in stating of Sidorenko conjecture and in definition of number of homomorphisms at sum by X, we separate vector of X with indexes corresponding to independent set of vertices from H, and we can copy other vertices from H by applying Cauchy-Schwarz inequality. So we can build induction transition from some graph to some mirroring of such graph, and assuming that that set of central vertices is independent set is very strongly Actually, we may consider other, assuming that center vertices induce a matching subgraph. It's obviously technique, obviously. Just build mirroring procedure, and after it build induction from one edge graph from K2 to some graph for which we want to prove Symmetry and Conjecture. Let us return to Shkredov's lemma and the extended conjecture as generalizations of Shkredov's lemma. For proof Shkredov's lemma, we use similarly procedure, but we have edge that intersect so-called mirror line that intersect axis of symmetry. And we can generalize this principle for all cases of mirrorings. For example, for such case, we can add the edges that intersect mirroring line, but we need to assume that such edges also formed matching subgraph. This is technical. This have technical reason, and again we can build induction procedure from graph K2 to any other graph. I will return Shkredov's lemma in first applying Cauchy-Schwarz inequality when we turn from energy equation to Cherry. We apply simple mirroring by vertex without edges that intersect mirroring line. This is transition from K2 to Cherry, and applying mirroring above is transition from Cherry to triangle. Interesting moment at this concept that we built a sequence of such mirrorings from K2 to K4 to fully graph on 4 vertices. And this allowed us to obtain proof of extended conjecture for K4. And it needs to be noticed that K4 obviously have chromatic number equal to 4 instead of chromatic numbers equal to 2 in Symmetry conjecture. And then, interestingly, open question, how to prove extended conjecture for some graphs each with arbitrarily large chromatic number. Other open questions presented on slide, and is how to generalize other methods for studying Symmetry conjecture to studying extended conjecture, and how to generalize Shkredov's lemma with arbitrary D. Last question turned out to a question about subsets of equations in right part of Shkredov's lemma as their we can see that not all equations in right part have conditions about equal to D. And it is interestingly how to describe all subsets for which we can add such condition. That's all.
Thank you for your talk. Are there any questions to our speaker?
Can I make a comment?
Yes.
Can I make a comment? Actually, two comments. First of all, I'd like to say that I'm very happy that Konstantin found very nice elementary proof, and I must underline that actually in the symmetric situation, his method works even better than the operator method, the original operator method is. There are other problems where you need asymmetric results, but in symmetric setting, it's perfect. And also, I would like to make a comment about the essence of the talk. So in my lemma, actually, I have a specific graph, rather dense graph, and I want to calculate the number of triangles in such graph. Of course, everybody knows that it's not possible to have a very dense graph to calculate the number of triangles. Take bipolar graph. But because of this convolution structure, as Konstantin named by multi
Convolutions multigraph.
Yeah, sense. You somehow can reduce this counting problems for triangles to counting problems for cycles, and for cycles of even length. And of course, you can calculate it easily using eigenvalues of the graph as I did, or elementary as Konstantin luckily found. But the reason is that in some specific situation, when you want to find triangles, don't worry, sometimes it's possible. Thank you.
No, I would like you to clarify some your notation in the very beginning. So it's like, can you open this? You have a slide with extension of the Iverson
okay.
notation. Just can you? I mean, in previous slide, I guess, yes. So it seems to me that if people do not know this notation or have never worked with this, it's kind of hard to grasp what happens here, even on this slide. So can you comment how to translate like this Shkredov lemma and with your notation? Because in your notation you have a function, at least it's written here, and then you have like 3 lines in the notation.
Yes, no. Here
But let's discuss just Shkredov lemma. I mean, that's so that.
In definition of extended Iverson notation, f is not function. F is some expression for many different with many different sets. Any expression.
So what is written then in the Shkredov lemma in the for example right hand side? That you are counting solutions of
counting solutions of.
So it can be written as a system, yes? What kind of a system?
This we enumerate values of each variable that marked by large symbols, we summing by all combinations of values of different large symbols, and we enumerate it by set A. And variables x, y, and z are fixed inside each system that summed.
So can I put it in such way that in the right-hand side in this sum, we compute the number of triples x, y, and z, such that x minus y, x minus z, and y minus z belongs to the set difference of A.
Yes.
Yes. And in the left-hand side, why do we need three lines there? Why cannot we put
so three independent? At left side we have three independent equation. In fact, cube of in fact it is cube of number of solutions to such to some one equation.
Sorry for interruption. You could write A minus A equals A minus A to the third. Yeah.
Yes, exactly.
Yeah. I'm very sorry that, you know, at least for me, this notation is new, and it was
yes, it's
hard
new.
to grasp what happened.
It is new notation.
And okay, thank you.